All right. So today is the second class for physics of transistors course. So we'll discuss crystal structure of semiconductors. Uh, and when we're talking about semiconductors, mostly in this course, we'll mainly focus on silicon, right? We'll mainly focus on silicon, right? And we'll discuss a little bit on germanium, gallium arsenide, and gallium nitride, because when we go to HEMT, we'll discuss about gallium arsenide and gallium nitride also. Um, so we'll not discuss about silicon carbide, gallium oxide, or diamond, uh, but I'll give you assignments to find out the crystal structure of these new materials. Right? Okay, so the first question is what is a crystal, right? So all of you might have heard about crystal. So if you look at the picture here, right, so this is the high resolution TM image of a silicon, and silicon come in a crystalline form. You see, the crystal is a material that exhibits perfect periodicity in the atomic structure, right? So if you look at this image here, right, so you see these bright dots, right? So the bright dots are nothing but atoms, right? And you could clearly see the atoms are perfectly arranged, right? And the distance between these two atoms we generally call lattice, means lattice constant. But so so basically the crystal is nothing but perfect means perfect arrangement of atoms, right? So crystal can be defined in terms of symmetric array of points. So if you take these atoms as points, we call them lattice, right? Basically, the lattice and crystal means are same, but in the lattice we just replace these atoms by points, right? If you draw in a piece of paper and you put points in a perfect periodic arrangement, we call it the lattice, right? Okay. So this is again a zoomed version of that same image. So this is a silicon crystal, and you could see that here the atoms are perfectly arranged. Uh, so the distance between two atoms is always same, right? Okay. So as we saw, the crystal is an array of atoms such that every atom has identical surroundings, right? So if you look at here, right, so every atom, if you look at each atom, so every atom has identical surroundings, right? Um, so the translationally periodic arrangement of atoms in space is called crystal. But translation means basically if you take a one atom and if you place another atom in one direction and go on placing atoms in one direction, basically then we could get a structure, right? A crystal, right? So um, unlike lattice, right? The crystals are 3D in nature, right? So basically, we do not have 1D crystals, right? One dimensional crystal or two dimensional crystals. So we have 3D crystals, right? But we could have 1D lattice and 2D lattice, right? Okay. So talking about material system in this device course and the transistor course, we'll mainly talk about three kind of materials. So one is crystalline. So crystalline material will so this is very important because we want the semiconductor material to be crystalline, right? So crystalline, also we'll talk about polycrystalline material here, right? So because if yesterday also I showed you the MOS transistor or bipolar transistor. Let's take example of the MOS transistor. In MOS transistor, your gate is polycrystalline material, right? This is not a crystalline. So polycrystalline is, so we have, so basically we have uh, multiple crystal arrangements, right? Crystalline arrangements, right? So and also we have amorphous. Amorphous is random arrangement of atoms. There is no periodic arrangement of atoms. So basically, when you talk about silicon, the insulators, right? Silicon dioxide, silicon nitride, or aluminum oxide, all those materials that you use in the semiconductor, in the transistor hafnium dioxide, they're all come in the amorphous form, right? So there is no periodic arrangement. right? So we'll mainly deal with these three material system: crystalline, polycrystalline, and amorphous. Okay, so here this is a very good example, because if you look at the MOS transistor, so yesterday I showed you. So if you take a MOS transistor, right? MOS transistor. So I have n plus here. Let's say, so take, if you look from the top to bottom here, if you take a cross section, so this is your metal gate, right? And this is made of polycrystalline, basically polycrystalline metal, right? And here I have oxide, this part I have oxide, and below I have semiconductor, right? So this picture here shows the cross section in this direction. So you could see polysilicon is a polycrystalline material, but if you zoom, you will see there is a crystalline arrangement in patches, right? So there is not perfect crystalline arrangement, but crystalline arrangement in patches, right? Then in the oxide part, you see this part here. This is amorphous silicon dioxide, because here, if you look at if you look at this image, you cannot really figure out any atoms, right? So there are random arrangement of atoms, right? So this is amorphous, right? Oxide is amorphous, right? And you have silicon substrate, and this is crystalline, right? Perfect crystalline, right? So modern solid state devices use all those forms of materials, right? Even you talk about bipolar transistors, so modern bipolar transistors, right? They have polycrystalline region, they have amorphous region, they have crystalline region, right? Similarly, MOS transistor, NMOS, PMOS, right? And also in the heterojunction transistors, this is a different system. We do not have polycrystalline materials there, but we have crystalline and amorphous material in the HEMT system, right? Okay. So again, this is so same thing. This is repeated. So crystalline, polycrystalline, and amorphous. Um, So if you see this polycrystalline region here, you could clearly see. So there are patches, right? So patches of crystalline arrangement, right? So this patch here, so this is crystalline, right? This patch again crystalline, but with a different direction. So right, and this part. So these are patches of crystalline, right? So this is not crystalline, but these are polycrystalline, right? So basically, we want our gate to be crystalline or crystalline material also, right? But because if you look at, right, so means I don't know if you understand microfabrication. So basically, how do you do this? How do you form the gate? So basically, if you have a p-type substrate here, right, you grow oxide, right? You grow oxide. So you oxidation process, you grow oxide, right? On top of that, you deposit gate material, right? So this is basically silicon. You deposit silicon. Since the silicon is deposited on silicon dioxide, it cannot take a crystalline form, right? So that's the reason it becomes polycrystalline, right? Right. But for better conductivity, we need crystalline metal. But since the silicon is deposited on top of silicon dioxide, we cannot get crystalline material there. We have polycrystalline metal. Okay, so all right. So why crystal structure is very important? Why you are studying about crystal structure, right? So basically, the crystal structure defines a couple of things, right? So basically, it defines the band gap, right? So depending on the crystal structure, you could see whether a material is metallic or semiconductor or insulator, right? So the crystal structure defines that, and also other properties like mobility. I mean, it's many other things, right? Mobility, conductivity, everything, right? That will depend on the crystal structure, right? So the material properties, the material properties of the semiconductor, because we are dealing with semiconductor mostly here. The semiconductor. material depends on the crystal structure, right? So the crystal structure is the main thing, right? So that's the reason you need to know about crystal structure. And once you know about the crystal structure, so you have tools. So let's say you want to know the band gap of the silicon band. So let's say you have you have material X, right? And you know the arrangement of atoms in that material, right? So you know the arrangement of atoms, right? So let's say you know the arrangement of atoms. So there are tools you could there are tools you could place those atoms and simulate, and you could find the band gap or other matter properties of this semiconductor, right? And basically these tools are ab initio tools, and ab initio tools, and they do DFT, means basically density functional theory simulations, right? So if you do DFT simulations, you could get but the input to that tool uh, is your crystal structure, right? So you have to give crystal structure, like let's say lattice constant, like so how the atoms are arranged. If you give these things to that tool, that will give you the band diagram on the metal properties of that semiconductor. So the crystal structure is very important, um, because it determines the material property of the semiconductor, and you are interested in material properties because you want to use those semiconductor to build your device, right? Build your transistor. Okay, so coming back to the type of lattice, right? So as I told you, the crystals can only be 3D, right? But we have 1D we have 2D materials also, right? We have means 2D materials also. So but when you talk about lattice, so we can have lattice. I mean, basically lattice is nothing but the periodic arrangement of points, right? So when you have periodic arrangement of points, you could make 1D lattice. The 1D lattice means you're just putting the points in one direction, right? So let's say this is direction X, right? You are just putting the points in a periodic arrangement, but in one direction. That is 1D lattice, right? So this 1D lattice is mostly described by a single lattice parameter, right? What do you want to know, right? You just want to know the distance between these two atoms or 2 points, right? If you know the distance between 2 points, you could make a 1D lattice, right? Right, right. So you just put the points separated by this distance, you'll get the 1D lattice. Unfortunately, there is no material system. There is no 1D material. I mean, till today. But in future, maybe somebody will come with 1D material, right? Similarly, 2D lattice, they are infinite in 2 dimensions, right? So they have generally 2 dimensions. So if this is X and this is Y, right? So if you take a point, so basically they are defined by 2 vectors, A and B, unlike 1D lattice. So basically if you know A and B and the angle, right? So basically 3 lattice parameters, right? A, B and angle between these vectors, right? Alpha. Then you could define a 2D lattice, right? So so they're infinite in 2 dimensions. So and the 2D lattice can be generated with this basis vectors A and B, but you need to know another parameter alpha, the angle, right? So what I'm telling here is, so if you know A, let's say A is 5 angstrom, right? And B is 5 angstrom, and alpha is let's say 70 degree, right? So then you could put the points now, right? So basically you take A, then uh, you know the B, right? So this is your A, right? Then you could put point B here because this is at 70 degrees. So basically 70 degree, then you could point B, right? So basically you can go on putting those things like this, right? So this is how this is how you'll build a 2D lattice, right? So you need 3 parameters, A, B, and alpha, right? So we have these 2D material systems. So it's nowadays, as I told you in the last class also, So people are talking about 2D material based FETs, right? So graphene, right? So let's say graphene, right? Graphene is a 2D material, right? So molybdenum disulfide. So graphene is a 2D material, right? Phosphorine, uh, we have phosphorine, uh, molybdenum disulfide or tungsten disulfide. So people have already demonstrated transistors with these materials, right? Molybdenum disulfide, tungsten disulfide, phosphorine, graphene, right? So they are all 2D materials, right? Okay. So this is 2D lattice and 3D lattice. So again, so 3D lattice can be generated by three basis vectors. So they can be generated by three basis vectors. They are infinite in all three dimensions, right? So they have x, y, z. The 3D lattice are generally described by six lattice parameters because you need A, B, and C. Let's say this x, y, z direction, the basis vector, as well as three angles, right? The angle between A and B, B and C, and A and C, right? This is how will you define a 3D lattice, right? So so 3D lattice. So we have 3D crystals, silicon, germanium, all those bulk semiconductor materials are 3D crystals, right? Um, okay. So here, so basically, so periodic lattice. So we discussed about three kind of periodic lattice: 1D, 2D, and 3D lattices. So so these periodic lattice can be described by something called unit cell, right? Um, so when I was telling you about that, let's say you want to use a ab initio tool, DFT tool to find out the metal properties of a unknown semiconductor. So the input will be the unit cell, right? So what is the unit cell of that crystal, that semiconductor? Once you give the unit cell, the tool itself could make the crystal, right? Because the unit cell is needed to make the crystal. So once you give the unit cell, the tool itself could make the crystal and will do the simulations and will give you the basic material properties of that semiconductor, right? So the definition of unit cell is this is the smallest building block of a crystal whose geometric arrangement defines the crystal's characteristic symmetry and whose repetition in space produces a crystal structure is called unit cell, right? So basically, if you take a unit cell and place it in x direction, if this is a 1D lattice or 2D crystal, then you take that unit cell, place it in the x direction and y direction, you will get the 2D crystal, right? Or 2D material, right? And if a 3D crystal, you take the unit cell and they place it in the x, y, and z direction with these basis vectors, whatever basis vectors are given, then you'll get that crystal structure, right? So basically, the unit cell is a representative unit of the structure, right? So basically, the unit cell is more than sufficient to generate the crystal, right? Right, and in a basically the unit cell will contain atoms, right? Right. So for example, here this is a 2D lattice, right? And the unit cell, so you could have different unit cell, right? So basically this part here, um, this can be a unit cell, right? You could take this unit cell here with an atom inside, right? And repeat it in the x and y direction, you will get the 2D material, right? So then this is defined as a, this is a unit cell also, right? Similarly, you could also take this as unit cell, right? So, right, but here unit cell contains one four atoms by one fourth of those four atoms, right. So basically 4 into 1 by 4, so uh, basically it contains one atom, but it's a different kind of unit cell, right? Even you could get that structure, get this periodic lattice using that unit cell also, right? Also you could define the other one, I mean, so you could but this is not the basic unit, right? So basically you could also, this red one here, you could also take it to generate that periodic lattice, right? uh, so so the, I think um, the concept of unit cell is clear. So unit cell is uh, um, the right. So this is the smallest building block, and you take that unit cell. If you know the unit cell, and you could place it in the x y direction for to have a 2D metal, or x y z direction to have a 3D crystal, right? Um, okay. So the property of the unit cell will define the properties of the solid, as I discussed, as I mentioned earlier. Um, so when you're talking about 3D lattices, right? So the 3D lattices are defined by three basis vectors, um, A, B, C, and alpha, and six lattice parameters, alpha, beta, gamma, right? So based on these six parameters, actually there are seven lattice systems and four lattice centrics, right? So um, so here um, should I mention? Yeah. So so basically, um, um, you have this is primitive. So basically, if you look at the 3D lattice, I'll not go in much detail here, but these are different. So basically, this defines a total set of crystals available, type of crystals available in the earth, right? Um, so we can have when you talk about 3D lattice, so there are seven lattice systems like triclinic, cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, and monoclinic. So basically, these are defined based on A, B, C, and alpha, beta, gamma, right? So if you take a cubic lattice, right? So when you take a cubic lattice, in cubic lattice, A equal to B equal to C, right? So here I could write A equal to B equal to C, and alpha equal to beta equal to gamma equal to 90 degrees, right? So this is a cubic lattice, right? So this is defined as a cubic. So this behaves as a cube, right? Similarly, if A, B, C are not equal, right? So here A equal to B in the second case, A equal to B, but C is different. So this is a tetragonal structure, but here alpha, beta, gamma is equal to 90 degrees, right? So that is a tetragonal lattice, right? Similarly, orthorhombic lattice where A is not equal to B, not equal to C. A, B, C, none of them are equal, but alpha, beta, gamma equal to 0, sorry, 90 degrees. So this is orthorhombic lattice, right? Similarly, you can have the triclinic where A, B, C are equal, right? But alpha, beta, gamma not equal to 90 degrees. That is orthorhombic. I mean, then you could have rhombohedral, uh, yeah, so rhombohedral, then hexagonal, and monoclinic, right? So these are different lattice systems, right? So there are seven lattice systems, but also uh, depending on the position of atoms, right? So there is four lattice centrings, right? So let's take example. So if I take a simple cubic lattice, so I take a simple cubic lattice here. Um, so if I take a simple, if I draw it properly, okay. So let's say this is a simple uh, cubic cubic lattice. So let's say A equal to B equal to C, and alpha equal to beta equal to gamma equal to 90 degrees. So, right. So, but depending on the position of atoms, right? So basically, if the atoms are simply at the corners, right? Right. So this is a simple cubic, right? Right. So that's why this is P, right? So this is a simple cubic or primitive, right? So this is a primitive lattice, right? Okay. Then in addition, if there is an atom in the middle of the cube, right? So middle of the cube, then that is called body centered, right? So basically, if you see here, so there are atoms at corners, right? If there is another atom at the middle, right? So this is a body centered cubic, right? So primitive and body centered cubic, and if so, there in a cube there are six faces, right? So we have six faces. So if in addition to the atoms in the corners, if there are atoms in center of each face, then that is a face centered cubic, right? So what we discussed, we have simple cubic or primitive. Let me write that as primitive, simple cubic or primitive, right? Then we talked about body centered. That means with addition to the atoms at the corners of the cube, there is an atom in the center. So that is body centered. Then we have face centered because the cube has six faces. Then each face has an atom, right, which is placed at the center. That is the face centered, right? And that is then the other one is base centered, right? So base centered is so there are two faces. Right. So basically, with addition to the atoms in the corners. So there are two atoms at each. So that is one at the bottom and one at the top, right? So a top face, right? So that is sorry, bodies base centered, right? So these are four kind of lattice centerings. So based on these seven lattice systems and four lattice centerings, so most of the crystals are means most of the crystals available in nature are divided into these lattice systems, right? So seven lattice systems and four lattice centerings, right? So so based on that, so let's say there are some example. So crystal system is cubic. So cubic crystals mostly your normal salt, zinc blend, copper. So they are normal cubic crystals, and uh, see these are the simple lattices. Um, like if you see tetragonal, so if you look tetragonal, then your white tins, tin oxide, titan oxide, calcium sulfate. Uh, so these are all tetragonal lattice, right? Uh, so also, I think I forgot to mention, if you see, so there are seven lattice systems, but four lattice centering, but there are not 7 into 4 28 because some of the systems are not found in the nature, right? So basically, this is not possible, right? So we didn't find anything here, right? And right, right. So so basically, these are the um, 3D lattices which are possible and available in the winds, right? So um, basically the crystal means you could define means basically different materials. So basically cubic, if you talk about cubic, your sodium chloride, zinc blende, copper are cubic crystals. White tin, tin oxide, titan oxide, copper, calcium sulfate, so they are tetragonal crystals. Similarly, rhombic sulfur, KNO3 and barium sulfate, so they are orthorhombic structures. So similarly, graphite, zinc oxide and CDS. So zinc oxide is also a semiconductor, and cadmium sulfide is also a semiconductor, but this is basically hexagonal, simple cubic hexagonal structures, right? So similarly, you could go through this table, right? Yeah. So I don't need to go through one by one. Okay. So these are basically lattice systems. We talked about 1D lattice, 2D lattice, and 3D lattice, and all the crystals are 3D in nature. Um, So, but the point is, what about silicon? Basically, we are interested more about silicon, right? But silicon is a diamond cubic, right? Basically, this is a cubic crystal, right? Silicon is a cubic crystal, but it's called diamond cubic because diamond cubic is a little bit different from simple cubic, right? So why it is called diamond cubic? Because diamond also has the similar structure as silicon. Diamond has the similar structure as germanium also, right? So so this is called diamond cubic lattice. So but the interesting thing is, so here in the silicon, this is the combination of two face-centered cubic lattice, right? So you have to, I mean, so I'll come, I have another slide to tell it very clearly. So just to uh, tell, so the silicon crystal is the combination of two interpenetrating FCC lattices, right? So you take two crystals and one crystal is penetrating other crystal, right? Right. So we'll come to that structure, right? So this silicon crystal can be constructed by taking two FCC lattices and placing the second one displaced by a by 4 a by 4 a by 4 basis vector. I'll come directly to it, right? So basically, let's say uh, in the right hand side, so you say this is a basic face centered cubic cell, right? What do you mean by face centered cubic? So this is a cubic lattice. uh, why it is cubic lattice? Because if you see here, a equal to b equal to c, that the right, and alpha equal to beta equal to gamma equal to 90 degrees. So this is a cubic structure. So you see there are atoms at the corner, right? We have atoms at the corner, right? And each face, there are six faces, and there are six atoms at the center of each face, right? So second phase, third phase, fourth, fifth, sixth, right? So there are six faces. So this is a FCC, right? So this is a face-centered cubic lattice, right? So if you take two of them, right? So basically you take two of these lattice and uh, penetrate, right? So basically, you could not clearly see it, but here, right? Here you could see it, right? So see, this blue one is one crystal, right? One lattice, FCC lattice, and the red line wala, that is another lattice, and you penetrate the next. So basically, the second, let's say this is my second lattice, and this is my first lattice here. So second lattice is displaced from the first lattice by a by 4, a by 4, a by 4 in both all directions, right? So x direction a by 4 shifted, b direction also a by 4 shifted, and sorry, y direction and z direction also a by 4 shifted, right? So basically, if you see, uh, it is something like this, right? So if I take in a view, right? So basically, I have one lattice here, right? And I have another lattice. So here is a 2D. So this is shifted a by 4 in this here, right? This part, and also a by 4, right? But if you look from the 3D's 3D way, so it will look like this, right? So also G direction also it will be a by 4 shifted, right? Right. So these are two interpenetrating FCC cells, right? And what you do is, so if you see here, uh, so how do you construct the silicon crystal? So uh, then remove. So you place these two lattices so shifted by a by 4, a by 4, a by 4. Then remove the atoms which are outside of the first cell, right? So you see, this was our first cell, right? So this is our um, let me do that, right? So this is our first cell here, right? right? So this is our first cell, and um, sorry, let me put. So these are the atoms in the first FCC cell, right? So each phase has a atom also, 6 atoms in each phase, right? So this is our first FCC cell, right? Then I have the second FCC cell, which is shifted by A by 4, A by 4, A by 4 here, right? And um, what I have done means what I have done here is, so basically the atoms that are coming, the atoms of the second cell which is coming outside the first cell, you remove it, right? If you do that, only 4 atoms from the previous from the second FCC cell will remain, and then this crystal, this is the diamond cubic crystal, right? So the diamond cubic crystal, if I come back to my original silicon crystal that I have shown you, so basically you see uh, the so there are two interpenetrated FCC lattices, but what is kept is only 4 atoms from the second lattice, because those 4 atoms are inside the first FCC lattice, right? Um, so this structure is very unique to diamond, right? Diamond is a crystal, right? So diamond is carbon, right? So diamond is a crystal, and so then the silicon also has the similar structure. That's why it is called diamond cubic, right? So this crystal, this crystalline structure is called diamond cubic lattice, diamond cubic crystal, right? So silicon is actually a diamond cubic crystal structure, right? So here, another thing is uh, the radius of silicon atom, which is 1.18 angstrom. The lattice constant is 5.43 angstrom. So lattice constant is this distance, right? 5.43, right? From the FCC cell, right? You take, right? So this is a cubic, right? So that's why all A, B, C are same, right? So these are all 5.431 angstrom, right? But the smallest spacing between two atoms will be 2.35. That is between this atom and the red atom, blue and red atom. So that will be through 2.3. But that is not the lattice constant of the silicon, right? The lattice constant of silicon is 5.431 angstrom. Okay. Any questions here? Is it means, did you understand? Is it clear?
Sir,
Yes, Shruti.
so the smallest spacing is like it is smaller than 2 times the radius. So what does it mean actually?
Smallest than 2 times of radius. Okay. The smallest spacing is this one, right? So basically, as I told you, right? So lattice constant is 5.43 angstrom, but this is the smallest spacing, right? The spacing is between these two atoms, right?
Okay. So it is not the distance between center of two atoms.
Uh, no, it should be the center between two atoms. Yeah. uh, No, okay. No, it is the center basically, but so basically, if you see, because this is okay, this is not a clear representative, right? So representative structure. So let's say, okay, you have a good point. So everybody should clarify. Let's say if this is the center of each atom, so your lattice constant is definitely uh, this one, right? 5.43 angstrom, right? Right, when I'm telling this is only smallest spacing between this is 2.35 angstrom. This atom here and this atom here is very close to each other, right? So they are very close to each other, right? So they'll be packed, right? So um, uh, right, so this is also center of this atom to center of this atom. This is 2.35 angstrom, or very close to each other, means they're touching each other, right?
Okay, sir.
Okay, so any other doubt? So is it clear to all? So what about you, Bhavesh?
Yes, sir, clear.
Aditya?
Yes, sir.
Okay, anybody else? Sarda, Nishant, you could get it, right?
Sir,
Yes.
so the earlier when you showed the centrings, they were I and C. They were used to represent body centered and edge centered.
Okay, let me go there. Which one?
So, in the previous slide.
Hmm.
So what is this I and C? For?
Oh, yeah. So I say I is the body centered cubic, right? So there are some crystals where there are atoms at the corners, plus there is an atom at the center of the body, right?
Yes,
So
that is clear. I just mean what is I, like what is the full form for the I thing?
oh, I don't know from where the symbol come from, because so you see these kind of systems are already developed in late like 1880 1890s, right? So what
Yes.
I stands for I don't know, but I stands for body centered cubic, right? So this might be abbreviation from a different language, right? So uh,
Okay.
yeah, so don't go by that. So I stands for body centered lattice, right?
Okay, sir.
And similarly the C stands for base centered lattice. Right? Okay. Anybody? All right. Okay. So if there is no questions. So uh, and please keep in mind. So germanium exactly have the germanium also has the diamond cubic structure, right? Like silicon. This is the silicon structure. Silicon is diamond cubic, and germanium is also diamond cubic structure, right? Uh, Uh, so basically, what we are interested, the material properties also depends on the number of atoms, right? So basically, we have a unit cell. Unit cell is the smallest um, um, smallest dimension, right? So basically, you could take a unit cell and create the crystal, silicon crystal, right? So if you take a silicon unit cell, so what are the number of atoms, right? So so this is a unit cell of silicon, right? So this is unit cell of silicon, right? So and you could take that unit cell and you could make a crystal, right? Let's say you want to find the band gap or metal properties of silicon, then you know this unit cell. You could create this unit cell. Basically, for to have that unit cell, you have to tell that okay, this is a diamond cubic, means cubic face diamond cubic structure, and you have to give the distance between the atoms, right? How the atoms are placed, right? If you define that and give that structure to your tool, a DFT tool, the DFT tool will do the simulation and give you the EK diagram. From there you could derive different metal properties, right? Um, so the first thing is the volume of the unit cell, right? So what is the volume of the unit cell? So volume of the unit cell you could calculate. This is a simple cubic structures, and you know that this is 5.43 angstrom, right? So the volume will be 5.431 angstrom into 5.431 into 5.431, right? That is the volume of the unit cell, right? Right, this is the cell volume, right? So number of atoms, if you want to calculate the number of atoms, if you see, so inside the atom there are four, inside the cell there are four atoms, right? Other atoms are shared, right? Other atoms are shared, right? Because if you look at this atom here, if you look at this atom here, right? So this is shared by how many unit cells, right? Okay, to go to simpler question, right? So if this is a face centered, because this atom which is at the center of the face, this atom is shared by how many unit cells?
Two.
Yeah, this will be shared by two unit cells, right? So similarly there are six atoms at the face, and all those atoms are shared by two unit cells. So there are, if you want to calculate the number of atoms, then each of these 6 atoms on the face are shared by 2 cells. So there will be 3 atoms total, right? Right. Similarly, corner atoms, you take a cube, the corner atoms are shared by 8 cubes, right? Basically, if you see, there will be 8 cubes, right? Right. So each of these corner 8 atoms are shared by 8 unit cells. So you could count them as one, right? And there are 4 atoms completely inside the cell, right? So total number of atoms in silicon, right, is nothing but 8 in the unit cell, right? 4 plus 1 plus 3, 8. And the volume of the unit cell is 1.6 into 10 to minus 22 per centimeter cube, not per centimeter cube. Then the density you could find, right? Density is, so in the silicon there are 5 into 10 to 22 atoms per centimeter cube, right? So if you take a 1 centimeter cube of silicon, so you have 5 into 10 to 22 atoms, right? So this is very important, right? So why it is very important? Because the conductivity of the semiconductor depends on the doping, right? So conductivity of silicon, so you change the conductivity of silicon by doping it, right? You will dope it, right? So maximum, so what do you do in the doping? So basically during the, let's say this is my uh, this is uh, this is my silicon atom, right? This is my silicon atom. If I want to dope it, right? So what I have to do, let's say I dope it by n-type arsenic, right? So basically I have to remove silicon and put arsenic, right? So basically this silicon will go, and at this place I'll have arsenic, right? So the density tells you how much you could dope, right? Basically the maximum doping, n-type doping means with arsenic that you could have is around 10 to 21, right? So that's why maximum doping you could have is 10 to 21 per centimeter cube, right? This is because there is only 5 into 10 to 22 atoms, right? And we could maximum remove 10 to 21 atoms without changing the material properties much, right? So basically uh, with arsenic we could have a maximum doping of 10 to the 21 per centimeter cube. When you go to the MOS transistor, you will tell that okay, your N regions are highly doped, right? Your source and drain regions. So those maximum doping is 10 to 21, right? You cannot go beyond that, right? Similarly, if I have a semiconductor which has only density is 10 to 18 per centimeter cube, right? If I have a semiconductor, your density of atoms is 10 to 18 per centimeter cube, then the maximum doping you could have is around 10 to 16 or 10 to 17, right? So that means that semiconductor cannot be very heavily doped, right? That means the conductivity is limited, right? You cannot really change the conductivity by a large amount. So the, okay, so that's why density is very important here. um, Now similarly, as I told you, germanium is a diamond cubic structure, but the gallium arsenide, this is also a diamond cubic structure, but the only problem is here there is a heterogeneous matter, right? We have gallium and arsenic, right? So the when I told you last time, right? So diamond cubic structure have 2 FCC lattice interpenetrating FCC lattice. So here also we have the same thing, but the second lattice is made of arsenic, right? So so the inside atoms are only arsenic, and the corner atoms and the face atoms are gallium, right? So this is also a diamond cubic, but we don't call it diamond cubic because diamond is not like, diamond has all the atoms are carbon, right? But since we have gallium and arsenide, this is called zinc blend crystal structure. So gallium arsenide is zinc blend crystal structure, but here the lattice constant is 0.565. So this is 0.565. And similarly, you could calculate the density. So density of atoms is, we have 4.42 into 10 to 22 centimeter cube. Density is less than, a little bit less than silicon, right? And this is atomic density. If you, from the weight perspective, this is 5.32 gram per centimeter cube, right? So let me ask you a question here, right? silicon, silicon, let's say silicon has a lattice constant of 5 angstrom. Germanium also has a lattice constant of 5 angstrom, for example, right? Right, and both are diamond cubic structures, right? So number of atoms per centimeter cube, will it be same for both or different? Will it be same or different? Om, what is your answer?
Sir, so they should be same.
Why they will be same?
Sir, because the volume of the unit cell would be same as the lattice constant is same.
Okay.
And sir,
Yeah, so they will be same, right? So because the lattice constant is same, so they will be same, right? So number of atoms per centimeter cube will be same. What about the density in terms of gram per centimeter cube? Which will be higher or they will be same?
It should be different.
Okay, why should it be different?
Because molecular weight of these two atoms are different.
Yeah, definitely. Germanium is bigger than silicon, right? So basically, germanium will have much higher density in terms of weight per centimeter cube compared to silicon, right? So so when I talk about density, so density depends on the what is the atom we're talking about, right? So even if their lattice constant is same, if you have a heavier atom, then the density will be different, right? So here gallium and arsenic, they are both are heavy atoms, right? So that's the density is 5.32 gram per centimeter cube, right? Okay. So here there is a summary of common semiconductor materials that we use in microelectronics industry. So silicon, as I told you, silicon is a diamond cubic. Germanium is also diamond cubic. But the gallium arsenide and indium arsenide are zinc blend structures. But gallium nitride is totally different. This is urzite, right? So this is a urzite crystal. I don't have a picture of, I don't have a crystal structure of gallium nitride. Okay. But if you look at the density of atoms, number of atoms per centimeter cube, because you see lattice constant, if you look at the lattice constant of silicon is 5.431. The lattice constant of germanium is 5.658. But gallium arsenide 5.653, but indium arsenide is a higher lattice constant, and gallium nitride has a lower lattice constant. So because of the lattice constant is different, the density of atoms, number of atoms per centimeter cube is different, right? Right. So you see, since the lattice constant is different in case of gallium nitride, so density of atoms per centimeter cube is higher in gallium nitride, right? Okay. But if you look at the density in gram per centimeter cube, you see germanium is higher than germanium. I mean, so weight of germanium, because germanium is a bigger atom compared to silicon. So your gram per density in gram per centimeter cube in germanium is higher. But gallium arsenide is similar to germanium. Indium arsenide and gallium nitride, they are heavy. Means density in gram per centimeter cube is different, right? So dielectric constant is mentioned here, right? So dielectric constant of I have to check. This is 151 or this is 15 point, right? For the indium arsenide, but dielectric constant is also depends on the crystal structure, right? Band gap is definitely depend on the crystal structure. So band gap of silicon, now we know that 1.12 electron volt, but the germanium is 0.68 electron volt. This is because as the number of the size of the atom increases, the band gap will reduce, right? Um, right. So we will discuss a little bit on that later. So And gallium arsenide has a band gap of 1.42 electron volt, is a higher band gap than silicon. Indium arsenide is a low band gap material. So that's the reason they are mostly used for IR detectors, right? Infrared detectors. We prefer indium arsenide. Gallium nitride has a high band gap, right? So gallium nitride has a band gap of 3.4 electron volt, right? Um, so this is much higher than silicon. That's the reason, because of the higher band gap, they could withstand very high voltages, right? Um, so they are used for high voltage applications, very high voltage applications, right? You could have transistors which could withstand 1000 volt, right, in gallium nitride. Electron affinity, again, the almost similar, but silicon, if you look at the silicon and germanium, their electron affinity is not much difference. Also gallium arsenide, the electron affinity is not also different. But indium arsenide and indium arsenide has a very high electron affinity, right? So it's very difficult to remove an electron from indium arsenide compared to silicon and germanium. Okay, so these are the crystal properties of some of the basic semiconductor materials. So as I told you, the material properties will depend on the crystal structure, right? So that's the reason when you do any investigation with the crystal structure, we call it ab initio simulations, right? So basically, let's say you discovered a material, you only know the crystal structure of that material, you don't know any other properties. So you have to do DFT simulation to get it, and those simulations are called ab initio simulation, very basic simulations, right? Um, so okay, so I think it's already 1 minute past 12. I'll stop here. We'll continue our discussion on Friday, right? All right. So if you have any questions, please let me know.